Yes, good morning, good morning, good morning, good morning. So, all fine? Good morning. All good? Okay. Yes. So, what we have completed in last examination, means in last class? Yes. All good, yes. What things we have completed in last class? Just, okay. Because I don't remember so many batches are there. So, okay, I forget in which batch what is there. So, what we completed, just give me some brief. VRMS, okay. So, in VRMS, how many questions? VRMS, how many questions we have done? In VRMS, okay, from there I will get the idea that 4 questions, 6 questions, 8 questions, 5, 6. Okay. I told you about the escape condition. Escape, when molecules will escape. This one not done, I think. Condition of when molecules will escape, presence of atmosphere, absence of atmosphere, this is not done. Different types of velocity we have written. Different types of velocity. Yes, different types of speed if I say. This is also not written. Okay. So mainly if I say, then we have done the question. In one question we change the temperature. In one question we change the mass. In one question we change both. One question was for dissociation, and later on we did 2 questions, increased to and increased by. I hope these were the questions. Increased to and increased by. Yes. Increased to and increased by. Up to these questions were there. Okay, so now we'll write one more question here on the VRMS, then we'll move forward. Okay, and this one is for you. You have to solve. They're asking. Okay, at what temperature? At what temperature VRMS of H2 will be equal to VRMS of O2 at 27 degrees Celsius. Okay, this is the question. Then we can say VRMS of H2 will be equal to VRMS of O2 at 27 degrees Celsius. Okay, at 27 degrees Celsius. So now we can say in this one VRMS of H2 is actually equal to VRMS of, okay, O2 here. Okay, so now we can say in this one VRMS of H2 should be equal to VRMS for O2. This is given in the condition here. Okay, and now we can see what are the formula for VRMS. If I say formula for VRMS is, you can see it is the root over 3R T1 by MW1, and here I can see it will be the root over 3 RT2 by MW2. Okay, if I do a square both sides, then I can cancel the root. Okay, root will be cancelled. 3R also I can cancel. Okay, so I can write finally I'm left with the T1 by MW1 equal to, we can say, T2 by MW2. We'll put the values here. You can say in this one T1, okay, if I say T1 here, then we can write T1 is actually in this one. If you say that is your, we have to find MW1 is for the hydrogen, it is the 2, okay, and now we can see in this one for oxygen temperature is 300 Kelvin, mass is your, okay, for the oxygen 32, okay. So now we can say it becomes 32. So from here, if you say, then you can write, so T1 actually becomes 300, this will be the 16, so 300 by 16 Kelvin. Calculation can you do? Can you do the calculation? Okay, so this is the Kelvin. We can convert into degrees Celsius. If they're asking the degree Celsius, then we can subtract minus 273. You will subtract, you will get answer in the degree Celsius also. Okay? Yes. So I hope this question is clear to you. Anyone having any problem in this one? Okay. So now we can say next question here. Okay, we'll write the next heading actually. Different types of, right, heading. Different types of speed. Okay, what type of speed is there? So we are going to write different types of speed. Different types of speed. Okay. Now, I can say here in this pen, molecules keep on moving randomly. And if molecules are moving randomly in all possible direction, molecules are moving randomly in all possible direction. So, are you getting in any particular direction? Is there any net flow? Net flow in any particular direction means in you can say molecules are moving effectively in this direction, or molecules are moving in this direction. Okay, is there any net flow in one particular direction? When molecules are moving in all possible direction, is there any net flow in one particular direction? Means I can say that, okay, molecules are moving in the x direction or y direction or in z direction. There is no net flow in any particular direction. It means if I take a net velocity or if I take average velocity or overall velocity, then what is the net velocity or average velocity? We can say, sir, v1 plus v2 plus v3 plus dot dot dot. Okay, and some is going, okay, some particles going this side with the 10, others are going with the opposite direction with the minus 10. Here going, okay, 20, then at 20. Overall summation is going to be 0 because there is no net flow in one particular direction. So what will be the average velocity of the molecules? Average velocity of the molecule is going to be 0. If I say velocity of the molecule is 0, velocity of the molecule is 0, velocity is not 0. Okay, velocity is non-zero, but average velocity, if I say, it is going to be 0. So we can write here number 1 here, average velocity. Okay, so you can say, sir, average velocity here in this one I can write, okay, average velocity, which is the basically your, okay, v average. I will put the arrow here for the direction, and we can say v1 plus v2 plus v3 plus dot 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 divided by n, which is going to be 0 because there is no net flow in one particular direction. So we can say v average is going to be 0 here. If I say what about the average momentum? Momentum is there. Each particle is having its own momentum. In the last class also I said momentum is there, that is your mv. But if I say average momentum, then what will be the average momentum? You can say, sir, average velocity is 0. So average momentum is also going to be 0 because we can write here in this one average momentum, that will be the delta P average. Okay, and we write as a small p for the momentum and capital P for the pressure. So we can say this one is also going to be mv average, and that is going to be 0. So they can ask, okay, on an average, which quantities are 0? Because average velocity is 0 and average momentum is 0. But if I don't take the directions here, if I only consider magnitude, and if only I am taking the magnitude, that is known as your speed. So if I take average speed will be 0 or non-zero? If I am taking only average speed will be 0 or non-zero? Average speed is going to be, average speed if I ask, non-zero. Okay, because if I'm taking only magnitude, then okay, so we can see here in this one average speed. Okay, yes sir, average speed is nothing but the, we can write here v average, and we can say v1 plus v2 plus dot dot divided by n. Okay, and this is non-zero, this will be having some value, so we can write, okay, from the Maxwell, okay, distribution we can find this velocity. Average velocity means average speed of the molecule here comes 8 by pi P by rho, means here the difference is your 8 by pi. Okay, so 8 by pi P by rho. We can say this one is here 8 by, okay, pi RT by MW, also 8 by pi RT by MW, or I can say this one is basically root of 8 by pi KT by small m. Okay, so it will be basically 8 by pi, okay, P by rho. It will be basically your 8 RT by pi MW, or we can say 8 by pi KT by small m. Okay, so these are the just differences, only 8 by pi. Only the difference is your 8 by pi. Other things remain the same. So 8 by pi P by rho, 8 by pi RT by MW, or we can say 8 by pi KT by small m for the average speed. Can we remember this formula now? Can you remember these things? Okay. So I will write the next one here. Okay, this is the your average speed. Okay, after the average speed we have here. Okay, next one is the VRMS, and for the VRMS already I have told you. Okay, what is the full form of this one? You can say, sir, this one is going to be root mean square, okay, root mean square velocity. So I can say if I directly add the velocity, then their summation is 0. So what I am doing, first of all, I am doing the square, okay, and if I do the square, then all the negative becomes positive. So before taking the mean or average, I am making, okay, positive. So velocity square, and then I will do the mean for them. Means if we have the velocity here v1, we have v2. So first of all, I'll do the square, v1 square, v2 square, v3 square. After that, I have to find the mean. So we can write plus dot dot. Then we can divide by add, and then finally we have done the square to so balance that. We are going to take root again. We are going to take this root again. So this is the VRMS. We can say VRMS equal to root of V1 square plus V2 square plus V3 square. This is also one more formula for VRMS. If I ask one thing, suppose V represents your velocity, okay, V is the velocity. If I say this thing, this, okay, this means your average, okay, so average velocity we have seen 0, okay. If I put like this, that means this is your average. So average velocity is 0 here. So this one is 0. But if I say this thing, V square, this will be 0 or non-zero, V square, because you know, if I'm doing the square, then square will make all negative edge positive. So this will be positive or negative. You have to do this thing, this V square, okay. This is non-zero, okay. This one is going to be non-zero here. If I say V cube can be 0, V cube can be 0, V cube. Yes, this can be 0, okay, V cube can be 0. But V4, if I say power 4, we'll say some power 4 also, okay, it will make all the negative into positive, so power 4 cannot be 0. Now we can say that if I take any even power will make every negative edge positive. And when every negative becomes positive, then even power cannot be 0. Can we write this thing? The even power cannot be 0 means we can write here in this one, even powers, okay, cannot be 0, okay. And what is the reason for this one? Because we know that even powers makes everything positive. That's why, okay, positive plus positive cannot be 0. So even power cannot be 0. Yes, this is clear. Even powers cannot be 0. This is okay. Now, so this is your VRMS here, and we know even powers cannot be 0. Formula for the VRMS already we know, okay. Once again I am writing, because all the time VRMS we have to remember. So this is the, okay, 3p by rho, this is the root of 3 RT by MW, as well as I can say this is the root of 3 KT by small m, okay. If I want to ask the question here, one simple question I will say here in this one, they will say that, okay, velocity for the molecule, okay, velocity for molecules, okay, for the molecules, they have given 1, 2, 3, 4 meter per second, okay. To take the simple calculation, I have taken 1, 2, 3, 4. To give the tough, somewhat, okay, more calculation, they can take 10, 15, 18, 28, like this, okay. So we can say here in this one, that find the velocity for the molecules, means 1, 2, 3, 4 is given, find VRMS. So yes, sir, if you want to find the VRMS, then this is a simple thing. First of all, for all the velocities, we have to do the square. So 1 square, actually you can say 1, 2 square is 4, then we can write 9 plus 16, divide by we can take 4, and then when we'll take finally root. So you can say 16 and 9 is the 25, and 25 and 4, 29 and 21, okay, that becomes 30. Okay, so this is the root 30 by 4, okay. So I can say root 30 by 4 if you have to calculate, okay, you can say root 30 by 4, and 30 by 4 we can say 15 by 2, that is the basically root of 7.5 meter per second, okay, root of 7.5. Suppose I am asking here V average. So we can say V average will be basically equal to 1 plus 2 plus 3 plus 4 divided by 4. So now we can write here 4, 3, 7, 7, 2, 9, 9, 1, and 10. So here we can write this one is the 10 by 4, and 10 by 4 is how much? Your 2.5 meter per second, okay. Done the things? Means this is question is nothing. If they are asking like this, we can do, okay. We can find the VRMS, we can find the V average, okay. So next speed that we need to consider here is the most probable speed, okay. Most probable speed they will say sometimes. So I will just move this one up, and then I will write here most probable speed. most probable speed. Okay, and for this one definition I'm writing first one. Okay, this is the basically speed for which, okay, speed for which number of molecules are maximum. Okay, speed for which number of molecules are maximum. Okay, so that is known as your most probable speed for which number of molecules are maximum. Is for this particular speed, okay, more molecules will be there. Molecules will be having some velocity like 1 2 3 4 1 3 5 6, means more number of molecules will carry that velocity or that carry that speed, that is basically known as your most probable. Like if I give you example here, suppose they have given the speed like this: 1 meter per second, 2 meter per second, 3 meter per second, 1 meter per second, 2 meter per second, 5 meter per second, okay, 1 meter per second, 6 meter per second, 2 meter per second, 8 meter per second, 2 meter per second, 7 meter per second, 2 meter per second. Now we can say in this one, if you see for the 2 meter per second, how many particles are there? For the 2 meter per second, we can say 1 2 3 4 5, okay, 5 particles are having 2 meter per second, and for the one we can say 1 2 3, okay, others are rest 1 1. So here we can say this one, okay, most probable velocity will be how much in this case? More particles are there for the 2 meter per second. More particle in this one, if you say for the 2 meter per second, and if 2 meter per second more particle means 2 is going to be your most probable. Okay, so we can say most probable is basically for which number of molecules are maximum. If number of molecules are maximum, that is going to be your most probable. Okay, okay. Now, again, when we derive from your Maxwell distribution, we are getting this thing V equal to, in this one, you need to remember that Vmp becomes here root of 2p by rho equal to, we can say, root of 2RT by MW equal to, we can say, it becomes here root of 2KT by small m. Okay, so in the RMS root 3 is there, in the average if you say, then in average we draw 8 by pi is there, and in this one MP there is the root 2. So this thing, you if you remember that root 2, root 3, root 8 by pi, we can easily remember all the formula, okay, for this one. Means if I say now here in this one that in RMS, you can say, sir, in RMS, okay, and if I ask RMS ratio of average, and then if I ask ratio of MP, so you can say in all these velocity, if you say RT by MW is common, RT by MW is common. So what will be the ratio here? You can say the ratio in the RMS. If I say RMS, we are getting here root 3. In RMS, root 3 is coming. In the average, root 8 by pi is coming. In the MP, root 2 is coming. What is the actually common? Your RT by MW. Means if I put RT by MW in any of the, okay, like root 3 RT by MW, root 8 by pi, root 2 RT by MW, okay, and don't cancel the root. Sometimes people cancel the root. People do like this. Sometimes, okay, they say that, sir, root x by root y. Root cancelled, x by y. Can we do like this? Can we do this way? Can we do? No, this time, okay, NTA did. You remember one question in which they have done this thing? One question of radius of gyration was there. Root 5 by 3. The radius of gyration, one question was there, na? Root they removed, and later on they have to give add mark. That question, radius of gyration, you didn't see in the paper? They removed the root, and later on they have to give the add marks. You cannot remove this root like this, okay? Some people give a reason. You are doing this way. You are writing root x equal to root y. Here you are cancelling. Here also I will cancel, okay? So I am not cancelling the root, okay? Again I am saying I am not cancelling the root. I am doing square both side. When I am doing square both side, it becomes your x equal to y, okay? So don't make this habit of cancelling the root. Yes, that question become the bonus mark, okay? That was the root 5 by 3. They, okay, written 5 by 3, okay? We cannot cancel root, okay, up and down. So we can say here in this one, you cannot cancel the root. You have to remember as it is, okay? Because some of, Okay, people might be thinking, sir, let's cancel the root. Okay, root is this because we are very we have this high efficiency in cancelling the things. Okay, let's cancel. So roots will not be cancelled. Okay, if I say which one is more, RMS or average or MP? So yes, sir, in RMS we have here 3. Okay, and here we have 8 by pi. 8 by pi, if you find, then how much will be the value for 8 by pi? Roughly you can tell. 8 by pi roughly what will be the 8 by pi? Roughly 2 point something will be there. 2 point something will be there. Okay, this 8 by pi, and this is the 2. So we can say, sir, RMS is going to be more. Then we can say V average, and then we can say this is the V MP. This trend you need to remember here. Okay, and for this one we can remember like this also: RAM, RAM. Okay, RMS, then average, and then then your MP. Okay, RMS, then average, then MP. Okay, then if they ask, they want to ask some question also, they can ask ratio based question like what is the ratio of RMS? Okay, they can say RMS to the MP. Okay, so RMS to the MP we can say it will be the root 3 by 2. Okay, root 3 by 2. Like this we can proceed for the questions. Okay, so I hope you have written these things. Okay, now we'll write next heading in this one. Okay, so this one you have to remember the ratio as well as this. Okay, which one is more, which one is less here. Right, Maxwell velocity distribution. Okay, Maxwell velocity distribution curve. Only curve I am writing here. Okay, Maxwell velocity distribution curve. Okay, yes. So these curves are plotted by Maxwell. Just we have to keep in the mind. Okay, here n and here your velocity written, and graph was like this. Okay, so in this one, if I say for this particular velocity, this region, this point tells here number of molecules are maximum, and your number of molecules are maximum for which velocity? Number of molecules are maximum for which velocity? Whatever I have told you, I just said na. So number of molecules are maximum for which one? Number of molecules are maximum for VMP. Okay, so you can say, sir, corresponding to this one is going to be VMP. So this one will be the VMP here. Okay, so from the peak of the curve, we can say that is going to be MP. From the peak of the curve, that is going to be MP. Okay, and after MP, if you say in this one, then what will come? You can say, sir, after MP, there will be the your RMS here. Okay, this will be the VRMS. Because RMS is bigger, okay, RMS is more than MP, okay, and after that RMS we can say here will be the your V, here will be, no, after not RMS basically, after that will be the V average, and then I can say V RMS, okay, out of 3, RMS is more, okay, so after the average and then RMS. Can I ask this thing that RMS is the, okay, can I say this thing that for RMS, okay, most of the molecule have velocity equal to RMS, true or false? Most of the molecule have velocity equal to RMS, true or false? Most of the molecules have velocity equal to VRMS. Maximum molecule have velocity equal to true or okay, that is false. Okay, most of the molecule have velocity known as most probable. Okay, most of the molecule have the velocity known as most probable. Number one thing is clear. Second question I am asking, most your RMS velocity is the maximum velocity. RMS velocity is the maximum velocity. RMS velocity is the maximum velocity. True or false? RMS is not maximum. RMS is maximum out of these 3. Out of these 3, RMS is maximum, but RMS is not maximum. Here, okay, graph does not stop here. Graph keep on going. Means here somewhere will get the V max, and somewhere here will get the V min. Okay, so RMS is not the max. Okay, RMS is not the max. Something will be V max. Okay, close to the, we can say, okay, very close to the infinity somewhere. Maximum will be there, and MP is the minimum. MP is not. MP is not a minimum. Okay, most probably is not the minimum. Minimum velocity is something here. Okay, something here. Out of three, only we can say out of three, MP minimum, RMS maximum. But other than three, also so many velocities are there that we cannot write. Other than these three that I have told you, so many are there that I cannot tell. Okay, maximum is there, minimum is there. Okay, so we can say VRMS is not the max and VMP is not the minimum. Okay, somewhere here minimum will be there and here will be the maximum. Okay. If I increase temperature, then all types of speed will increase. If I increase temperature, then all will increase. Okay. If I increase temperature, then all will increase because V proportional to root T. V proportional to root T, so all type of speed will increase. Either you say RMS, okay, root T is coming, either you say MP root T is coming, either you say anyone root T is coming. So temperature more, speed will be more. So next question I am going to ask for means next graph here that, okay, I will be giving this graph at the different temperature. Okay, so this is the end and this one is the temperature T1 here. I will change color and then I will go for, okay, this one, and this one is at the temperature T2 here. And then I can say this one is basically at the temperature T3 here. Okay. Now you have to tell me which one is more, which temperature is more, T1, T2 or T3. We can see that it is, okay, better. I can say this one is here T1, T2, T3 means which velocity is more, basically T3. So directly I can say T3 is more. But from where you will find, actually you cannot, okay, compare from here. We have to compare from the peak, which corresponding to the peak, we can say this one is the VMP of first, this will be the VMP of second, and this will be the VMP of third. Okay, so from the peak we can always compare because I cannot exactly locate RMS, I cannot exactly locate average, but MP I can exactly find from the peak. So we can say from the peak, this is the V1, this will be the V2, V3. This much is the V1, this much is the V2, and this much is the V3. Of course, we can say, sir, V3 is more than V2 than V1, which indicates T3, then T2, then T1. I hope this thing you can do. Yes? Can we do the things? Can we write next? Next question. Means next things here, okay? Do you know that there is one escape velocity? Escape velocity means basically that velocity required to escape. Means if that much velocity I give to you, you will escape from the atmosphere. Okay, you will escape from the surface of Earth. Okay, and if you remember, what is the escape velocity for the surface of Earth? Escape velocity for the surface of Earth. Any idea? Escape velocity from the surface of Earth. Any idea? If you don't remember, no problem. Okay, just I'm asking. Okay, not 13.2, it is 11.2. Okay, 11.2 kilometer per second. Okay, 11.2 kilometer per second. Okay, means 11,000 meter per second. It is the huge speed. 11,000 meter per second. Okay, right now if okay, we are going with the 100 meter per second, 50 meter per second. Okay, 11.2 kilometer means you're in 1 second. Okay, 11.2 kilometer, huge. Okay, 11,000 meter. So now we can say if that much velocity is given to you, you will escape from the surface of Earth. Molecules are moving. Okay, what actually makes the atmosphere? You can say, sir, atmosphere is basically made of gases. Okay, and mainly which gases I can say? Mainly here we can say your nitrogen is there, 78% oxygen is there, as well as some other gases makes this atmosphere. Okay, and all the molecules are moving with some velocity, like hydrogen at the room temperature moves with the around 2000 meter per second. 2000 meter per second. Okay, hydrogen. And for the escape, what is required? 11,000 meter per second. So hydrogen can escape. Hydrogen at the room temperature is having only 2000, while requirement is 11,000. It is moving with the 2000 hydrogen. Okay, hydrogen speed is the max. Okay, speed of hydrogen is max and limit is the 11,000. Okay, so at right now any molecule is going to escape from the surface of Earth. Right now any molecule is going to escape from the surface of Earth. No. Why? Because their speed is less than escape. Okay, because whatever the requirement for escape, okay, requirement for the escape is 11.2 kilometer per second, and whatever the speed they have right now, that is very less. Okay, hydrogen is only 2000, which is the maximum. Oxygen will be even lesser than that. All other gases will be less. Okay, so they cannot escape. That's why all the gases are present in the atmosphere. And when all the gases are present in the atmosphere, so we can say atmosphere, this is the condition of presence of atmosphere. But if I increase the temperature, if I keep on increasing the temperature like this, okay, I'm increasing the temperature, so your VRMS will keep on increasing, and at some temperature what will happen, VRMS will be equal to escape, and when VRMS will be equal to escape, then all the molecule will escape. Okay, and when molecule will escape, then atmosphere will be present or absent. If all the molecule escape, then atmosphere will be absent. Okay, so I am writing the two conditions here in this one. Okay, number one is, okay, I am writing here presence of atmosphere, and now for the presence of atmosphere you have to tell me in this one what should be the condition for the presence of presence of atmosphere. VRMS should be more or less. VRMS should be more or less. Presence of atmosphere, VRMS should be more or less V escape. Okay, VRMS should be less than V escape. V escape I can write V escape. If less, then they cannot escape, so all will be present. Okay, and if I write here in this one that the absence of atmosphere, so you can say absence of atmosphere, I can write in this one. Okay, that VRMS actually becomes more than or equal to V escape, then molecules are going to escape. Then molecules will escape. Okay, then molecules will escape. Clear? If VRMS is more than V escape, then molecules will escape. So these two conditions you have to remember: presence of atmosphere as well as absence of atmosphere. So molecule will escape when VRMS is more than or equal to V escape. If I ask one question, okay, calculate temperature at which, okay, at which H2 will escape from Earth. Okay, from Earth. Okay, so now we can say we have to solve this question: find temperature at which H2 will escape from Earth. So we can say, sir, this condition we have to write VRMS should be more than or equal to V escape, and if I am solving, then we can write the equal. Okay, so I can write VRMS is how much? Root of 3 RT by MW should be more than or equal to 11.2 kilometer. I can write 10 power 3 meter per second. Okay, V escape for the Earth is 11.2 kilometer per second. You can write, okay, V escape for the Earth is 11.2 kilometer per second. Okay, if I do square both sides, then I can write here in this one 3 RT by MW is more than equal to 11.2 square will be 125 into 10 power 6. Okay, if you multiply the 11.2, roughly I can say 125. And 121 will be the 11 na, so 125. If I put R value, then R is how much? R value, what value of R I should put here? R. I'm asking what value of R you have to put in this one. You have to put 25 by 3. And what you will put? MW. MW you put for hydrogen. For hydrogen mass is 2 gram. So you will put 2 into 10 power minus 3. Now tell me the answer. MW is 2 into 10 power minus 3. Now tell the answer. 2 into 10 power minus 3. 2 gram, na? So you have to convert into kg. So what will be the answer? Temperature you have to find. You have to find the temperature. Solve fast. But ultimately in the examination you have to do. Yes. 10 power 4, everyone got that is the correct answer. So because we can say R is 25 by 3, so that will be the 25. T divided by MW 2 into 10 power minus 3 more than this one 125 into 10 power 6. We can say this one becomes here 5 and 5 into 2 will be 10. So T if you multiply then will be more than or equal to 10 power 4 Kelvin. If temperature becomes this much, temperature of the surface of Earth becomes this much, then all the hydrogen molecule will escape. This one we have calculated for the hydrogen. Can you do the things? 10 power 4 is how much? 10,000. If 10,000 Kelvin will be the temperature, then molecule will escape. Okay, and right now you know the temperature is almost maximum. Okay, temperature is how much? Maximum temperature we are going up to 50-51 degrees Celsius. So there is no problem. Molecules are not going to escape. We don't have to worry much. Over. Can you do the next one now? Next question. Next things. Okay. Right, next heading here. Degree of freedom. Degree of freedom. Degree of freedom. Degree of freedom. What are the meaning of degree of freedom? Basically, that how freely you can move. Like if I say I can move in this plane, I can go I can move in the x-axis as well as y-axis. So I can freely move in the two-dimensional. So for me, degree of freedom is 2. We can say If I say suppose like Iron Man is there. So Iron Man can move in the Iron Man can have some exhaust here and then like this can fly. So it can move in the x, y as well as z. So how many degree of freedom will be there for the Iron Man? For the Iron Man, degree of freedom will be how many? 3 degree of freedom is 3 na? No? 3 degree of freedom. If I say suppose some insect is there and that insect is moving on this wire like this here moving like this, so we can say it is moving along one dimension. So we can this is your degree of freedom is 1. Now we don't have to find for these things, we have to find for the molecule ultimately. So we can say molecule can move from one place to other place, and moving from one point to the other point is known as translation. So molecule can have 1 degree of freedom in the translational degree of freedom. Translation molecule can do from one point to other point. Next thing is basically your molecule can when molecule is moving from one point to other point, then molecule can rotate also. Molecule doesn't move like this. This way it will not be moving. When molecule is moving, then it will keep on rotating. Molecule will keep on rotating and then it is moving. Like if I take your O2, so O double bond O, so it will keep on rotating and then moving from one point to other point. So rotation is also there. There is the rotational kinetic energy involved with the molecule. Some of the molecules will be having vibration also. Along the bond they will vibrate. They will keep on vibrating like this along the bond. So this is known as your vibrational vibrational degree of freedom. We can say that here vibrational kinetic energy will be there. So vibration is also there. So these are the things we can say rotation is there, translation is there, vibration is there. But vibration generally does not happen at the lower temperature or room temperature. Vibration gets only active at the high temperature. Vibration is there, but that is insignificant. It only becomes significant in significant at the high temperature. Karthik Puppala, Hi sir, how are you? I am in MBBS. Good. Enjoy. Because of you. Not because of me, because of your hard work. Okay? Because of your hard work, you are there. Okay? And there, keep on doing the hard work. Wherever we'll reach in the life, okay, that is okay, because of our hard work only. Yes, blessings are there. Okay? Blessings of your parents, blessings of your teachers, blessings of your relatives. Okay? So blessings from all the people, but hard work, okay, that is only done by you. Okay? So wherever you will reach in the your life, that is just okay. So, and we need to enjoy our hard work also. So I can say translational degree of freedom. Okay, three types of degree of freedom are there: translation, rotation, as well as vibration. Yes, can we write the things? First, we can say, sir, what is the definition of degree of freedom? Definition is how freely I can move. Okay, how freely I can move. Yogi, I am also in MBBS. So all the people from MBBS are attending the classes. Those who are in the MBBS, they are only taking the class. Remaining people are chilling. Okay. So now we'll write here in this one. Number of independent ways in which molecule can move. Number of independent ways in which molecule can move. This is a definition of degree of freedom. Okay, degree of freedom definition: number of independent ways in which molecule can move. Okay, now for the movement of the molecule, we need the energy. So you can say molecule can move or can have the energy. You can write in the bracket can have energy. Molecule can move or can have energy, because for the movement we need the energy. Okay, without energy you cannot move. Okay. If I say that you have to move from one point to other point, of course you cannot move without energy. To do anything in the life, we need the energy. So we can say molecule can move or molecule can have energy. So now we'll write here in this one. Number one, here I am writing in this one, translational degree of freedom. Translational degree of freedom. Okay, you can write any molecule can move in three different direction. You know that any molecule is there that can move in the space, and moving in the space means basically that is having x, y as well as z, x, y and z. So any molecule can move in the x, y, z. So we can say any molecule, okay, can move in three independent direction, x, y, z. So translational degree of freedom for any molecule is 3. Any molecule can move in three independent axes. So translational degree of freedom, Ft equal to 3. Okay, Ft equal to 3. Okay, Ft equal to 3. Okay, if I say that what is the energy in this one, so total energy if I write, then you can say half m Vx square plus half m Vy square plus half m Vz square. Half m if I take common, okay, then we can say this becomes, sir, Vx square plus Vy square plus Vz square. Okay, and Vx square plus Vy square plus Vz square I can write as the V RMS square. Okay, this one I can write as the V RMS square. So we can write here in this one half of m into this is the V RMS square. Okay, in x component, y component, z component, if I add, then this is the resultant is V RMS. And if I put the value here half m, V RMS is how much? Your 3/2 kT. No, means not means here. Okay, we can say VRMS formula. How told you? Okay, VRMS. If I write here, then you can say, sir, VRMS equal to root of 3 kT by small m. So I will put a square of this one. So 3 kT by small m. Small m will be cancelled. So we got here 3/2 kT. Okay, 3/2 kT. And if 3/2 kT is basically in for all three dimension, for x, y, and z. Okay, for x, y, and z, 3/2 kT. It means for this one half kT, for this also half kT, and for this also half kT. So energy of a molecule in each degree of freedom is how much? Energy of molecule in each degree of freedom is half kT. Energy of a molecule in each degree of freedom is half kT. Energy of a molecule in each degree of freedom is half kT. This is the statement given by the Maxwell that we will write okay, later on, that energy of a molecule in each degree of freedom is half kT, okay. Energy of molecule, okay, in each degree of freedom is half kT, okay. Now we'll go for next one here. That is the, okay, this one is about the translation. Now we'll say about the vibration, okay. So we can say for vibration actually, okay, vibrational degree of freedom, so taken at, or we can write here, considered at high temperature, considered at, okay, high temperature, okay. We will take only at the high temperature, considered at the high temperature, okay. Normally we don't take, okay. For example, if I say, for example, okay, for O2, okay, for O2, you can say O double bond O, okay. So in O double bond O actually, okay, we can say in this one, this bond I can assume like the your okay, spring, and if bond is like the spring, then how many energy are there in the spring? How many energy will be there in the spring? One kinetic and one potential, so two are there. So we can say for this one, okay, vibration will take how much? Your 2 degree of freedom. One mode, okay, and one mode, okay, one mode and 2 degree of freedom. Each mode of vibration, each mode of vibration, okay, each mode of vibration, okay, how 2 degree of freedom. 2 degree of freedom is one for the kinetic and one for the potential, okay, one for the kinetic and one for the potential. Each mode of vibration carries 2 degree of freedom, one for the, okay, one for the kinetic, one for the, but this one we take only at the high temperature. If I say monoatomic, in monoatomic, okay, if I say for monoatomic, any bond is there or not there? For monoatomic, any bond or no bond? For monoatomic, there is no bond, okay, and if there is no bond, then there is no vibration, okay. Bond, if bonds will be more, degree of freedom will be more, okay. Along each bond we can take modes and then we can calculate. So, okay, in question they will say, but for O2 you can remember that for the O2 each mode of vibration with the 2 degree of freedom, okay. Now I will draw the table. That table you have to remember here, okay. So I'm going to, okay, write the next thing here, add. So I will write the table here. Okay, here I will write, okay, FT means translation. This is the FV, this is the FR, and this is the total F we have to remember ultimately. Here I am writing the monoatomic and monoatomic examples. Already you know that the helium, neon, like this, okay. Then we have here diatomic, and for the diatomic we can say examples are O2, N2, okay, like this, dot, 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 okay. And then I can say here in this one, next one is your, okay, polyatomic. And in the polyatomic, two types are there. Polyatomic linear, some of the gases are linear and some are the non-linear gases, okay. Most of the gases are non-linear. But some, okay, like example, if I say CO2, then CO2 is the polyatomic, but it is the, okay, so polyatomic linear, okay, and I'm writing example for this one is the your CO2, okay, CO2 here, and then we can write here polyatomic non-linear, polyatomic non-linear, okay. Most of the gases are non-linear. For this one you have so many examples. You have CH4, you have NH3, okay. So many, I cannot write all the things, okay. If they give nothing, then we'll take linear or non-linear. If they have given nothing in the question, then we'll take linear or non-linear. We take, if nothing is given, we take all the time non-linear, okay. Translation for any molecule is 3, 3, 3, okay. Doesn't matter whether light molecule or bulky molecule, for any molecule translation is 3 all the time, okay. Translation is always 3 for any molecule, okay. Vibration, I said we don't consider, okay. So we don't take at the room temperature. We only take at the high temperature, so I am writing your vibration as 0, 0, 0, 0. Okay. Yes. And rotation is only there whenever moment of inertia is non-zero. Rotation only happens when moment of inertia is non-zero. So for this one 0, for this one we have 2, for this one 2, and for this one 3. And so total we can say 3, 5, 5, 6. So directly you can remember, okay. If you want a detail of the rotation, then I can tell, okay, that is your choice. Do you want a detail of rotation, or we can remember? Choice is your detail. No one is going to ask. Just we have to remember this 3, 5, 5, 6. 3, 5, 5, 6. Okay. Do we need detail of rotation, or we can remember? We can remember. We've got, okay. So 3, 5, 5, 6. Okay. This breakup, if you can remember, very good. That, okay. That 2 rotation, 3 rotation. Okay. Okay. We can remember. So we'll go for, okay, next one. Okay. 3, 5, 5, 6. This thing is very important. We are going to use here as well as in the thermodynamics 3, 5, 5, 6. So we'll write the next heading in this one. Okay. That is the Maxwell. Okay. Maxwell equipartition of energy. Maxwell equipartition of energy. Okay. Maxwell equipartition of energy. Maxwell equipartition of energy. Okay. Right statement. Energy of a molecule is equally distributed. Energy of a molecule is equally distributed. Okay. What he said basically that in all degree of freedom, equal distribution is there. And for each degree of freedom, how much energy is there? For each degree of freedom, how much energy is there? Just now in the previous one we have written for each degree of freedom energy is half kT. So he said energy is equally divided in all degree of freedom. Energy is equally divided into all degree of freedom, and energy for each degree of freedom is half kT. Energy equally divided into all degree of freedom. Energy of each degree of freedom is half kT. So right, energy is equally distributed in all degree of freedom. In all degree of freedom. In all degree of freedom. In all degree of freedom, and energy for each degree of freedom, and energy for each degree of freedom for a molecule is half kT. Okay, energy for each, okay, degree of freedom for a molecule is half kT. So what we got here in this one, the energy, okay, is equally distributed, equally divided into all degree of freedom. Okay, equal distribution is there. Okay, and energy for each degree of freedom is how much? Your half kT. Energy for each degree of freedom is how much? Your half kT. Yes. So if I say, sir, energy of each degree of freedom for a molecule is half kT. Okay, so I can write energy. Okay, energy for, okay, all degree of freedom for a molecule, all degree of freedom for a molecule, for one molecule for 1 degree of freedom is half kT. So I know that there are the f degree of freedom. A molecule can have f degree of freedom. It can be 3, 5, 5, 6 f degree of freedom. So energy for all degree of freedom for a molecule, then you can say, sir, for all degree of freedom is for f degree of freedom, I get f by 2 kT. F by 2 kT, we can multiply with the f. And if for 1 degree of freedom is half kT, so for f degree of freedom is f by 2 kT, because f degree of freedom is f by 2 kT. Yes. For one molecule, for 1 degree of freedom is half kT. So we can say for f, okay, for f degree of freedom, this will be how much? F by 2 kT. Okay, if I say here in this one, energy, okay, energy for, okay, all degree of freedom for n molecules. For n molecules means basically for all the molecules. So yes, sir, we can multiply with the n also. So we can write here F by 2 NKT. Okay. So this was the energy for all degree of freedom for n molecules. N molecules means basically for all molecules. Okay. So energy of the molecule for all is the F by 2 NKT. And you know, this one is basically total energy. Energy for all degree of freedom, for all degree of freedom, for all the molecule F by 2 NKT. So we can say this one is basically known as your internal energy or total energy. Okay, this one we can say internal energy or total energy. Okay, we can say total energy, or we can write here in this one internal energy. Okay. That one is basically equal to F by 2 NKT. This formula we got from the Maxwell, the total energy or internal energy U equal to F by 2 NKT. But some of you will say, sir, we have heard this thing that PV equal to, okay, PV equal to nRT. Somewhere we have done this one, that PV equal to, I can write here, PV equal to nRT, and which is also equal to n KT. PV equal to nRT or n KT. Is in place of nKT, what I can write PV also as well as nRT. So this formula becomes F by 2 nRT, or I can say F by 2 PV. Okay. So this is the formula of total energy or internal energy, F by 2 nRT or F by 2 PV. Okay. F by 2 nRT, F by 2 PV, F by 2 NKT. Okay. If they are given the mole, if moles are given, then I am going to use F by 2 nRT. If they are given number of molecules, I will use F by 2 NKT. If they are given pressure and volume, I will use F by 2 PV. I am going to use F by 2 PV. Okay. This thing clear? F by 2 nRT, F by 2 PV, F by 2 NKT. Can you remember? Okay, so we'll stop here because questions now we have to start on this one. Questions will take time also, so not going okay for the questions now. We can do later on, okay? But today we have completed the VRMS, all the questions related to the VRMS, okay? Till this one you can complete all the questions, okay? Yes. Can you do? And this thing you have to remember, okay? In the next class, you will tell that we have done the Maxwell energy formula we derived, okay? This formula we derived, and then after that we have to write the things. So we'll start directly numericals here. And degree of freedom, you have to remember 3, 5, 5, 6. Because without that one, we cannot do the things. Okay, so bye. This is your QR here. Now enjoy, okay? Do your questions. Yes, bye.